Okay, so for the last couple days, we've been working on Mr. Antoine Lavoisier's rule, showing that matter cannot be created or destroyed. And in order for us to follow that rule, we have had to learn how to balance equations and practice that over and over and over again. Today, we're going to take it one step further. So we can show that the number of atoms is the same before a reaction and after, but does the actual mass stay the same? If you remember back from the very beginning of the year, mass is the amount of matter in an object. So really mass is a measurement of matter. So we should be able to show that the mass of the reactants is also equal to the mass of the products. Well, in order to do that, we kind of have to learn some new things, and one of those is being able to measure what the mass is of these different particles per mole. Well, that word mole probably is new to you, so let's talk about that. That's a chemistry word right there. Okay, and it really has to do with counting things. So if I say that we have a dozen eggs, how many eggs do we have? 12, right? And if we have a pair of eggs, we have 2. Well, if you have a mole of something, you have 6.02 times 10 to the 23rd of whatever that is. So if we have a mole of eggs, we have 6.02 times 10 to the 23rd eggs. That is 602 billion trillion eggs. That's a lot of eggs. Okay, why do you think that chemists use this number, this mole, to count things? Why don't we count atoms in dozens or pairs? Well, the biggest reason is because atoms are so teeny tiny that when we have atoms and we're seeing what atoms make up, when we see matter, there is billions of trillions of atoms that are put together to create what we see around us. So in order for us to count them, we have to use really big numbers. Well, instead of, counting, 6 billion trillion every time, we came up with this unit to kind of make it easier on us called a mole. So how big is a mole? It's hard to imagine 602 billion trillion eggs. Okay? So the number again is 6.02 times 10 to the 23rd. If we had 6.02 times 10 to the 23rd paper clips, it would circle around the world 400 trillion times if we put them end to end. Okay? If we had a mole of marshmallows, they would cover the planet to a depth of 12 miles. 12 miles high of marshmallows in every direction on Earth, covering the whole surface. If we had a mole of seconds, that would last so long that the universe would die before we got to count all those seconds. And if we had a mole of marbles, they'd fit into the Grand Canyon, and there would still be enough left over to displace all the water in Lake Michigan and a few other lakes. So that is a lot. 602 billion trillion marbles. That's a lot. Computer can count at a rate of 800 million counts per second. If we can count 800 million counts per second, it would still take 25 million years to count up to the number 6.02 times 10 to the 23rd. Okay? If we had a mole of hockey pucks, the mass would be equal to the moon. And here's a big one, all right? Each human being has about 60 trillion cells in their body, and our population on Earth is about 6 billion. So that means the total number of living human body cells on Earth is about half of them all. All the cells in all the humans on Earth is about half of what a mole is. That really gives you an idea of how small that mole is, or how small atoms are, sorry. If 1 mole of pennies were divided among every person on Earth, we would each get 1 times 10 to the 14th pennies. And if on Earth, $1 million was spent every day of those pennies, it would still last 3,000 years. But life would not be very fun because we'd have 400 meters deep of pennies covering the entire Earth. It's a lot of pennies. So the point here is that the mole is a really, really big number. And again, the reason why the mole is such a big number is because atoms are so small. So when we count them, there's a lot of them there. Okay, if we have 1 mole of water, that means that we have 6.02 times 10 to the 23rd molecules of water. Just like when I said we had 1 mole of eggs, that was 6.02 times 10 to the 23rd eggs. So 6.02 times 10 to the 23rd is 1 mole of anything that you're talking about. It's just usually we talk about molecules and atoms when we're talking about moles. Okay? Now, with this idea of a mole, we can find out if we have a mole of a certain element, how much is that going to weigh? So we know that if we have 1 mole of carbon, that is 6.02 times 10 to the 23rd atoms of carbon. But how much will that many atoms of carbon weigh? Well, there is a nice shortcut for this, and that is that the atomic weight of each element is actually the molar mass. In other words, that's how much 1 mole of that element will weigh. So take a peek at your periodic table and find out what is the atomic weight of carbon. Should be the number at the bottom of the box, and you'll see that 1 mole of carbon actually weighs 12 grams. See if you can find copper to find out how much will 1 mole of copper weigh. 1 mole of copper weighs 64 grams. Again, you can round these numbers to the nearest whole number. Copper actually weighs 63.55, but I just went ahead and rounded that up to 64. And 1 mole of silver, which is Ag, will weigh 108 grams. Okay, so to find out the mass of each element for 1 mole of that element, you just look at your periodic table. Okay, so that's nice and easy. Well, not everything that we find is just a single element. A lot of times we put elements together to form compounds or molecules. So in order to figure out how much the molar masses of a compound or molecule, you just have to add up the molar masses of each part of that. So in a CO2 molecule, we have 2 different atoms, 2 kinds of atoms. We have carbon and we have oxygen. Okay, we're going to find out how much mass the carbon is contributing and how much mass the oxygen is contributing to this whole thing, and we'll just add it together because that's total all the parts of this molecule. So start off with carbon. Okay, how many carbon atoms are in this molecule? Well, there's 1. We know that because there's no subscript right here, so that tells us there's 1. And each carbon atom weighs how much? Again, look at your periodic table, and you'll see that the atomic mass of each carbon atom is 12 grams. So we'll take 1 atom that weighs 12 grams, we multiply it. That means carbon is contributing a total of 12 grams to this molecule's weight. Okay? Oxygen is the other element in here. So let's calculate how much mass is oxygen contributing here. This time, how many oxygen atoms do we have? The subscript tells us that there's 2. And each of those oxygen atoms weighs how much? If you look at your periodic table, oxygen atoms have a molar mass of 16 each. So 2 atoms, each weighing 16 grams, means that the oxygen is contributing a total of 32 grams. Okay, so carbon, 12 grams of mass is being contributed to this total molecule, and oxygen, 32. Well, if we want to know how much the whole thing weighs, all we got to do is add this up. 12 plus 32 gives you a total of 44 grams. So a CO2 molecule is going to weigh 44 grams for every mole that you have. Okay, let's try another one. Here we have aluminum oxide. All right, we have 2 different elements in here that we need to add up the mass for. First one being aluminum. So aluminum has how many atoms in this compound? And that would be 2. Each aluminum atom, if you look at your periodic table, take a second. If you need to pause the video, do it so you get used to finding the masses in your periodic table. But each aluminum atom is going to weigh 27 grams, meaning that aluminum, if you multiply 2 times 27, will give you 54 grams in this compound. Okay? Oxygen is the other piece in this compound, and oxygen has 3 atoms. You can tell that from the subscript here. And each of those oxygen atoms, just like before, oxygen always has a mass of 16. 3 times 16 is 48. So aluminum is contributing 54 grams to the total mass here. Oxygen, 48 grams. To find out the mass of the whole thing, we just add them together, and we get a total of 102 grams. So aluminum oxide has a mass of 102 grams for every mole that we have. This last one, I want you to try on your own. Okay, this is copper hydroxide. What I did is I just split it up by color here. You're going to want to add up the mass of copper, and then the mass of oxygen, and then the mass of hydrogen, and then get the total for the whole thing. I would pause the video, do it on your own, and then once you have it completed, check your answers. So copper is contributing one atom here. There is no subscript right next to this copper, so that's just one atom. Each copper atom weighs 64 grams, which means copper is contributing a total of 64 grams because you just have one of them weighing 64 grams. Oxygen is the next one. Remember that if you have a 2 outside of the parentheses, you have to distribute that to everything on the inside of the parentheses. So oxygen, you have 2 of them, each weighing 16 grams, which means oxygen is contributing 32 grams to the total. Hydrogen is the last one. Again, 2 times 1 will give you 2 hydrogens, each one having a mass of 1 gram. That means hydrogen is contributing a total of 2. And to get the total overall mass, you are going to add them up, and that gives you 98 grams. Okay? If you have any questions on these notes, make sure you ask, get some clarification. Otherwise, you have some practice problems to do in your notebook. If you get stuck at any point, make sure you raise your hand.